Hello, everyone. Today we are going to discuss machine learning algorithms, and we are going to discuss several general issues related to machine learning, as well as we are going to make some definitions on what we are going to study in future lessons. So if we speak about machine learning, first we need to mention some common tasks related to the field of machine learning, and we can speak of clustering tasks. So if we have some unlabeled data, we need to clusterize it to some defined classes that describe the data set properly. We can perform classification. And again, if we have some data set based on this analysis, on the analysis of this data set, we need to assign some new entries to classes that we have in this data set. And of course, we have regression. So we having some trends, we need to predict values based on these trends. And I would like so we need to define what we are going to discuss later in the course. So we are going to discuss, first of all, supervised learning. So if we have some data set in which we have features of the data, and we have some target variable, we try to make a machine learning model to get a machine learning model that by using the features predicts the value of the target variable, may it be house price or some material or catalyst or molecular property. And so, of course, there are other categories of machine learning tasks that are studied in the field of computer science. So we can speak of unsupervised learning. However, we are not going to discuss it in any significant detail. And there is semi-supervised machine learning in which both unlabeled and labeled data are used. And there is the field of the approach of reinforcement learning. And this is related, of course, in the new field of artificial neural network training. And we are going to mention reinforcement learning briefly. However, as long as we aren't going to use artificial neural networks in our upcoming workshops, we will discuss this tangentially. And in the beginning, I would like to suggest you several books and courses. And for those of you who feel themselves as true beginners in the field of machine learning, I can suggest the book called Machine Learning Simplified by Andrew Wolf. And basically, it has no prerequisites except for the knowledge of some statistics and calculus. And it gives foundations of and basics of supervised machine learning. It's clear and simple, and well, it has really illustrative examples, and you can download it free by following the link in the presentation I've sent you. Next, we are going to mention some examples from the Python data science handbook, and considering this book, I suggest you to follow this link to find Jupyter notebooks that illustrate the concepts considered in the book. And also you can follow the course msu.ai I've told you about before, and follow other courses by the Intellect Foundation. And we need to discuss what a machine learning project is. There are several stages in the project. So, of course, in most projects, we start by data extraction. So, if we consider chemistry-related tasks, we may search chemical databases or chemical literature, some research literature, or if we can even take and extract data, take laboratory notebooks and extract data from them. It happens, and nobody should underestimate experimental data from laboratory notebooks, because these usually contain data on negative experiments. And well, we're going to mention it later, why it's so important. And of course, we need to prepare data for machine learning, and analyze the data set to come up with features of the data that are representative of the phenomenon we are going to study, and that are easily, or that can be used for machine learning. So this third stage is model building, and in which we, of course, need to select algorithm, loss function, perform machine learning, evaluate model, and this can be this stage may include a closed loop, so we can we can select one model or another, one algorithm or another. So it's usually it's usually a trial and error process. So next, of course, is model validation. And here I should mention that for the previous stage in which we tune hyperparameters, the so-called grid search is often used, which we are going to mention a little bit later today. For those of you who want to get an understanding what grid search is, you can follow the link here and find the notebook on GitHub. So you'll by following the link, you will find the notebooks, and you can get an understanding of what the grid search process is. Briefly, we are going to discuss it later. So, and of course, there is model deployment. And here I would like to ask you, so what is the most difficult and time-consuming stage, in your opinion? What do you think?
If no one else is willing to answer, may I do it?
Sure, you can. You're encouraged to.
Of course, it depends. It depends on the complexity of the model. If our model is very complex, then selection of architecture for it, not so much for machine learning, but more for deep learning. Then selection of architecture, selection of hyperparameters, its evaluation and the training takes really a lot of time. But if we go a little bit deeper than that, then data cleaning and feature design can be really time consuming. If we have a good clean data set, it doesn't mean that there are no outliers. And hunting for these outliers can take a lot of time. So it really depends on the quality of our data set and the complexity of our model and the task we are trying to solve.
Yes, you are correct. And yes, it depends on the project. And quite often, the second stage of data preparation is the most time-consuming. Of course, I can imagine a project in which data extraction is time-limiting. For example, if you need to extract data from some analog sources, or if you need to poll people, which may take some time, but the second stage is quite often the most time-consuming. It's as it's called the least enjoyable, and it's also an error-prone stage. And in my own experience, a bad data set indeed can kill, I would say, an ML project. So, yes. And before diving into machine learning, I would like to mention, for those of you who begin their way in the field of machine learning, I suggest to study what principal component analysis is. So it is a method. It is a method that is commonly used to reduce data dimensionality, visualize data. If we want to, in case we want to find some clusters in our data set, we can perform noise filtering and feature selection. So basically, I suggest you use this notebook to get an understanding of what principal component analysis is. In a nutshell, however, and you can follow search Wikipedia for the article in which there is math related to this topic. But in a nutshell, we analyze the data set for vectors that describe the maximal dispersion in some direction. And first we fix the vector that has the maximal dispersion along it. Next, we go to orthogonal vector, and we may continue in case of many-dimensional, in case of a many-dimensional data set. Speaking of machine learning, we also should define the basic concepts related to the field. So if we train some model, if we are building some model, we can get several cases. First of all, we can get an underfitted model in which the model basically predicts the trends poorly. So it may be for a number of reasons, and in some cases, we select features which do not adequately describe the data. So we are going to speak about feature selection a little bit later when we are going to have some practice with Jupyter Notebook related to this lesson. And we can, next we can get an opposite situation of overfitting when the model is artificially sensitive to small perturbations in input data. Of course, we should seek a balanced model. And speaking of the balance, we should mention the so-called bias-variance trade-off. So if we complexify the model, and I'm going to show you a little bit later how it can be done. So we can complexify the model, and during the model training, we are going the error on the training data set, how the model predicts values in a nutshell. So how the model predicts the values in the training data set. So the training error will decrease. However, the error on the test data set will gradually increase after increase significantly after some point. So this will get us to an overfitted model from some degree of model complexity, and we should always seek the balance of the model complexity that gives us equal accuracy on both training and test data sets. Here, I would like to give you a homework for those of you. So I suggest you downloading this book by following the link I've given you before. And in chapters 3 and 4, I suggest you reading about the rich regression method. So we are going to use a rich regression in in 2 upcoming workshops, and I should mention that a rich regression with kernels, so it's kernel-rich regression, is actively used in chemistry now for a number of reasons, and we are going to discuss why as well in more detail in our workshops. Of course, I should mention artificial neural networks, and as some of you may know, the general topology, the general features of neural network training. Indeed, artificial neural networks are used actively now, and related to their use, as I've told you about, there is a field. So speaking of their use, there is a field of deep learning, and if we speak of that, we should define what deep learning is. And so indeed, in this field, the so-called deep neural networks are used with large numbers of the so-called hidden layers of neurons, and in deep learning there is a special approach to the training. So we are going to pay close attention to the so-called feature engineering and analyze our data sets in a way to find features that are representative of our data sets that can be used to build accurate machine learning models. However, deep learning takes a quite different approach, and usually minimal or no feature engineering is expected. So the data should be as raw as it can be. And in the field of deep learning, there are several approaches, several topics that should be mentioned. So in some studies, people use variational autoencoders that we are going to mention tangentially for chemical tasks. So if we speak of a model of some molecular properties, we need to train a neural network that output of which generates us the so-called latent space of molecular features in which we can, for example, perform some optimization. And we need to train a decoder that generates us the molecular structure from the output of the previous stage. And also we can speak of generative adversarial networks. And we are going to mention one work in the field of GAN application in chemistry in our last lesson. So now we are going to use the Jupyter notebook I've sent you to get an understanding of what exploratory data analysis and machine learning, supervised machine learning is. So for this lesson, I've selected a data set from Kaggle that I will the data set on diamonds prices, the so-called diamonds prices data set, which has features of diamonds and their prices, basically. I intentionally selected a data set that has no straight relevance to chemical tasks for a number of reasons. And the first one is that here I want to focus on machine learning as it is. And later, in the upcoming lessons, we are going to analyze and use data sets that are related to chemistry. So now we are going to use a representative data set with sufficient number of entries to build sufficient number of entries to have a representative exploratory data analysis and to build several models. So here I provide you with the link on some guides. First of all, we need to import several libraries. Of course, we need to import NumPy, SciPy, and Pandas. And also, we are going to monitor progress of several tasks. So here we import many algorithms from the scikit-learn library. So, and also we are going to use CatBoost. Also, we are going to use Plotly, as I've told you about. It has a number of features that make it outstanding for and very convenient for data visualization. So let's load our data set, download it from Kaggle. Here I provide you with a link. And yeah. So let's get some brief statistics on the data set. It has several features related to diamonds. And first of all, features like carat, cut, color, quality, etc. We are going to discuss these features a little bit later. And please note that the data set has numerical as well as categorical features which define how the so-called cut, color, and clarity. And we have no undefined values, unspecified values in our data frame. So yes, we read it as data frame. And there are none. Let's see what we've got in this pandas data frame. So first of all, the cut is related to defines how the diamond was cut from a stone, let's say. So the features of the polyhedron that is basically the gem. And it has identifiers and carets, so we can sort the data set. And let's cut out the identifiers. We aren't going to need them. So let's have a look on the features. First of all, the mass. First of all, mass. That is measured in carats. So it's 0.2 grams. 1 carat is 0.2 grams. And basically, if with the increase of the size, the mass increases as well. So one of the main questions is, does the price increase concomitantly? There are two linear size features, which are table and depth. So we have table and depth. And also clarity, and also we should mention clarity, that is specified with the following abbreviations. So FL for flawless, IF for internally flawless, and etc. So if there are some inclusions in the gem, the clarity gradually degrades. So if we have bigger inclusions or some defects, we have lower and lower grades through very slightly included, and included. So if we if there are clearly seen impurities, we can get I1, I2, and I3 grades. So I have, and next we can mention colors. We can also define color of a gem by using the following letters. So it gradually changes from completely colorless to light yellow. So let's analyze this data set and get some statistics. So we can get mean values, standard deviations, minimums, quartiles, and maximal values by using the following command, by using the following method. Let's visualize feature distribution in our data set. So here we have counts and mass. clearly we have the distribution is far from normal. So we have many modes, and also we have some clear outliers. So by the way, as I've told you about, Plotly allows us to make interactive figures, so we can get specific values, and we also can customize fonts, font sizes, etc. So let's make a plot of depth distribution. So here we have a distribution that is that at least looks like normal. And so it has bell shape. However, let's test the hypothesis of data if let's test the hypothesis if the data is normally distributed. So here we use the SP stats normal test, and you can find documentation easily, but briefly, it analyzes the distribution of the data on skewness and kurtosis. So ideally, in the case of normal distribution, we should get a perfect bell shape. However, our distribution can be different from the perfect bell shape by being positively or negatively skewed. It also can differ. It also can exhibit some kurtosis, so it can also be positive or negative. So we can the base of the bell can be thinner or thicker. So we can use SP stats normal test and analyze the distribution for skewness and kurtosis. And well, obviously, the distribution is not normal. Next, let's look if we have any linear correlations between our numerical features. So, and let's see. For example, we can see that there is some clear correlation with linear sizes and the mass expectedly. And also there is some clear correlation of the price with the mass of a gem. So let's see the distribution of our categorical features. And here we can assign color codes to the categorical features related to the clarity. So we encode this with color codes. Let's do that, and we need to wait a little bit. So, although we can do this to get a better representation. So, clearly, there are gems of different clarity of some specific colors. And so by analyzing the data frame, we can get the glimpse of what distribution do we have. And we can also visualize it, the distributions. So here, for example, we see that each color has gems of different clarity. So we can expect that the gems with bigger defects or with more defects have lower price, and purest gems has the highest price. Let's see. So first of all, let's make a violent plot to analyze the distributions. So here we have here we specify clarity, and we see that for each class we have some outliers. Also, we have main clusters of data. So we can analyze the value. So there is no significant, there is no clear dependence. And let's try data normalization. So we divide mass by price to get price per carat. And we need to wait a little bit till the plot is generated. So here it is. Clearly, there is no clear clear pattern in data even after the normalization. There are many outliers, and clearly the distribution are far from normal. And also, let's analyze if there is any correlation between price and normalized carat value. So value per mass. We need to wait a little bit again. And again, we have no clear correlation in the data. And of course, here we have a significant portion of outliers, which are some gems that are overpriced. So, what can we do? We can make a new feature to differentiate between moderately priced and let's say that differentiate between the main clusters, the main parts of distribution and outliers. So we need to we try to find outliers by constructing a new feature. We need to wait a little bit for that. And by the way, when I have a minute, I've told you about that. I've told you that data analysis and preparation can take a lot of time. Here we have exemplary task. However, in a real research setting, exploratory data analysis that will allow us to understand the data at hand can take even months. So here we have a new feature, our price. We introduced two new features. We introduced new features that allow us to differentiate between outliers and data from close to the mean values. Let's do some machine learning because we are running out of time. By the way, considering the your question about the code, you can and are encouraged to ask questions in the chat in the group. so you are free to ask questions related to the notebooks. First of all, let's use linear regression to build up some simple model of the data. So for those of you who feel themselves as beginners, I suggest you visiting to reading the book I've told you about, and or enrolling in some courses. So we would like to feed data with a line by using linear regression. And here, let's discuss what we are going to do. First of all, let's use standard scalar for data. I've told you, I'm going to tell you a little bit later. So let's select features. We select numerical features for our linear regression model, and we shuffle the entries, the data set. Next, we are going to use the standard scalar. It's for exemplary purposes here. However, in further examples, we are going to need scale data for sure. Basically, our features may be of different scale, and if we use some model that using features of different scale may degrade quality of the model by making some features artificially more important than others. So, and we select the target feature here. Next, we are going to split our data set into two subsets. And we split into train and test data sets.
One question about this. For what reason it is needed to dissect samples on test and
train data set. Train and test data sets. Basically, we need to do this because we aim to build a model that can make predictions on new new data. So if we have some unknown gem, if we have a gem for which the price is unknown, we need to build a model that can predict its price by its features, by its size, mass, or its purity. And basically, this is our main goal here. And if we include all entries in the data in the trained data set, we can check accuracy, and basically our accuracy estimation will be invalid because we used this data for training. So we've fitted our model on every particular entry from the trained data set. There is no prediction here. Generalizability of the model is the goal, so to speak. So by making a general model, we can make accurate predictions. So here we make a fit by using the trained data set with model features and prices, with the gem features and prices. And we analyze accuracy by using the R squared. And here I need to suggest you Googling what R squared is. The Wikipedia has really illustrative article with a figure. So R squared closer to 1 gives us indicates model of nearly ideal accuracy. And here we have R squared above 0.8, which is quite good. However, we can compute mean error. So we use trained model and predict values. Predictions have some errors, and we can compute mean from them. And we can compute standard error as well. So it's discussed in the basic course on statistics. And we have mean error that is close to 0. However, standard error indicates that we have a lot of outliers which price of which cannot be predicted properly. Next, let's visualize the predictions and actual data. So we plot actual values or data prices from the data set against predicted values, or we can flip it. However, a line of best fit, so best fit would be, ideal fit would be if predicted value is equal to the actual value. However, here we have a lot of, clearly we have a lot of outliers. So note that blue circles are predictions on the train set, and importantly, red circles with a dot are predictions on the test set. So clearly our model predicts prices poorly. Let's convert our two categorical features to numerical labels. So basically, I will show you later how I do that. So how much time do we have? Yeah, we are running out of time. Let's visualize. So we encoded color and clarity by using numbers, by using integers. And we are going to use them for model training. And again, we compute R squared and get R squared close to 0. This means that that our model basically doesn't work. And this might be expected given the fact that we used a basic algorithm as a linear regression. Let's try using random forest regressor to predict prices of diamonds. So for math and the features of random forests, you can refer to the book I've told you about, to a notebook, and also you can refer to the lesson on classic machine learning by the from this course by the Intellect Fund. Again, we do the same sequence. We use a label encoder, and we select features. So we encode categorical features and select price as our target. So we split again the data set into test and training data set into 8:2 proportion, and we can start. Yeah. We can perform machine learning. So here we get the picture which is much closer to the one I've told you about. Pay attention to the red dots. Basically, we have a distribution in which predicted values are much closer to actual values in the data set. So our model is much more accurate. So we can get a much more accurate model by using random forest. I should mention several algorithms that are normally used for classifications. However, all of them can be used for regression tasks as well. So, speaking of classification tasks, briefly, we need to assign unknown data to the classes based on their features. What can we do in our context? We can use support vector machines, support vector machine to assign, to check, to predict if the gems under consideration are overpriced or not. You can get a glimpse of what SVM classifier is by following the link. And basically, we try to divide data by a line or a hyperplane in case of highly dimensional data by maximizing this margin between clusters of data. So again, we select features and split the data set and start the training. Here, I introduce the concept. So the accuracy of classification can be analyzed in terms of the so-called confusion matrix. If we predict, if we assign some gem to overpriced or normal classes, we can assign gems that aren't overpriced correctly and get true negative values. We can get true positive values by false positive values by assigning normal diamonds to overpriced class incorrectly. Next, we can get false negatives. So if we if an overpriced gem is predicted to be non-overpriced, and of course we can get true positives. So when an overpriced gem is assigned to be true, to be overpriced, and so we can here we have true negatives, false positives in the following order. So we have quite significant proportion of false assignments here, and of course we can analyze accuracy on the test set, and well, you can see that of course on the train set we have a situation like if the model might be more accurate than it actually is. In the context of classification, we can also have the KNN algorithm, and this I leave it to your homework. You can analyze the code. So briefly, it can give us higher accuracy. And by the way, if you want to get a glimpse of what KNN algorithm is, you can refer to the MLS book here. So, and what is what can be new to what is new to what is unexpected to some people is that KNN can be used for there is a KNN regressor, so we can use it to predict price by from numerical features. So
and what is the abbreviation for SVM?
Support vector machine. Yes, thank you. Thank you for the question, and thank you for the comment in the chat. About the end jobs. For me, this well, I do it intentionally. However, of course, you can use all computational power. You can use all yes, you can use all threads that are accessible to that the process the CPU has. However, I prefer to has n jobs lower than the number of cores. Yes, yeah. Thank you. Thank you for mentioning this. So we can use KNN, which is K nearest neighbors, and build a regression model that is going to fail. Well, basically, we have a huge number of incorrect predictions, and the number of incorrect predictions grows with the incorrect prediction. There are higher percent of incorrect predictions for higher price gems. And at the end, I should mention CatBoost that can be used for regression tasks. There is a link in the notebook on a brief article about the features of CatBoost. Because we are running out of time, I suggest you reading this at home. However, we can discuss it later in the Telegram group. The so-called killer feature of CatBoost is that it allows us using categorical features in regression tasks natively. So again, we can start the learning. And here, I would like to discuss the following. So the notebook is called Node.js. Here, I meet grid searches that were used for hyperparameter tuning. When you when you perform machine learning, you usually define hyperparameters of the selected model. The main feature of CatBoost is its native, so it can natively deal with categorical features like colors. So here we include color and clarity in the training and test datasets. We can visualize, and we see that accuracy on the test set is even higher than in the case of in the case of random forest that we used before. So thank you a lot for staying here with me today.